what has been my experiences running this benchmark over different machines a long time and seeing things that are quite different, much more different than that I really expected. So in order to compare those machines, at BSc many years ago we developed a very easy efficiency model that tried to compute how efficiently you are running, let's assume an NPI application, okay? So if I have an NPI application, basically I can have my time can be split in two regions, time that I am computing, that in this picture is dark blue, at times that I am communicating, that in these pictures are in red, okay? So I can do either computing or communicating a long time. And I have multiple processes. In that case, to simplify, I will have two processes, okay? So using any profile of NPI, I can see how much of my time I'm doing computing, how much of my time I'm doing communication. In that case, half of my time I'm doing communication. Some profilers of NPI will tell you, okay, your problem is NPI. Well, I do not agree with that, and you will neither agree with that. Because I see on the first iteration, the first guy complete the works earlier and have to wait for the second one. The same happened on the second iteration. Over each iteration, there is some balance on my work that makes some time in NPI that is not really transferring the data. So I cannot blame to NPI part of this NPI time. Okay? So now with this picture, I see this is no balance. This is the difference of load between the different processes, and this is communication. Okay? So now I cannot blame I am dominated by NPI. It's, let's say, it's only 1/3, 1/4% of my time. Okay? So that's the way we measure, and that's the way I have used to compare the machines, is I compute the power efficiency, that is the percentage of time I'm doing computation, that is my goal. My goal is not to communicate, it's to compute, okay? As the product of these two numbers, the load efficiency, the load balance efficiency, the global load balance efficiency, and the communication efficiency, okay? This is the model I will use in this presentation, but in fact, just to clarify, this model has a little bit trick. Let's assume I have this scenario, okay? As a difference with the previous one, and the first iteration is the first guy, the same one, but is waiting the second one. But on the second iteration, it's just the other way around, okay? If I compute the previous model, I will say this is perfectly balanced, and I may blame API. But again, I know there is time in API that I cannot say it's API, okay? In this case, this load balance is compensated a long time, okay? And then this means if I compute globally with a profile, I will say this is perfectly valid, but there is time in communication that is not really communication time, okay? So my model really is the product of these three numbers, but as I said, this is just to clarify. In these slides, in this presentation, I will use the simplified model that you can use with any machine using any profile of NPI, so you don't need to use my tools. In order to do that, you need to use tools like Gimenez or other tools that have prepared to split the time inside NPI. So let's say the initial goal of this presentation is that experience I have for the trainings, preparing trainings. So when I have to do a training, the user selects the machine I have to use for the training, and I typically ask them to provide me with an application they are interested in. Because my goal is that if I present you the results of some code you are familiar, then that will be easier for you to follow, okay? But this is not quite frequent. So in many cases, the audience is spread, or they do not have any special interest in any application, and in that cases, I use Blueless. Blueless is a benchmark, so it's an efficient code from Lawrence Liverpool that it's my favorite default application. And the reason because it's my favorite default application, first reason is because it's very simple to install. It's a simple sparse code with no large input cases and so on, so it's quite simple to install. It works in most of the machines, very simple. Half an hour, 10 minutes, you have that running on any machine, okay? And I know what it should be great. Basically, this is the first parameter views. Here I have a histogram, so those are my NPI ranks. This is the things of instructions, so more to the right, bigger number of instructions. So basically I see vertical lines, meaning all the processes very well balanced, all the processes doing the same amount of instructions, except for that region, okay, that has variability with respect to the instructions, okay? So I have a perfectly balanced application, except one region, okay? And this is the one region, this is this black hole, for this kind of thing that is an all-reduced code, okay? And all the other communications used to be fast, which are point-to-point communications. Okay, I see 1, 2, 3 iterations, point-to-point communications with large computing phases, and this unbalanced region before the over-reduced. Okay? So this is the structure I know. But the nicer feature for me on LULES is that it requires a cube number of processes. Okay? And this means, well, I use 8, I can use 64, but it's even nicer to use 27. Okay? Because basically there are no sockets size 27, there are no nodes size 27. So I push a little bit the machine saying, okay, I'm not an easy guy. I'm not going to ask you 16 or 24, I'm going to ask you the 27 processes. And let's see what you do that. Let's see how do you mark that. Okay? So what I initially expected with this approach is that, okay, my code is almost perfectly balanced state 1 region. This reason that I do not have this size will make some small unbalance, and I will see how it is managing the resources. Okay? So I expected some extra unbalance because this nice number that is not easy to split, but only that. And those are my results. Okay? I have some other numbers, but basically these more or less distributes. These are the 3 numbers I had on my previous slide for efficiencies. Okay? And these are the numbers I get for the different applications. The higher the better, and this is kind of colored like a traffic light. So if you are green, you are good performance, 19 are in dark green. I have a lighter green for the 80s, still good, so I don't need to work on performance. Okay, I think it's good enough, considering I spend less than 20% of my time doing the computation, that is, the communication, that is the overhead I have to pay to run in parallel. Okay, 70s are orange. I start to be concerned. I'm starting to have 1/4 of my time doing this overhead of running in parallel. Okay, and then the reds got under 17s because it's a huge percentage of time I'm running in NPI. Okay. One thing I have to warn you, as I said here, so higher number doesn't mean to be faster machine. Okay, because basically consider you have a platform like the blue gene architecture where the processor is slow, the network is fast. Okay, this means my percentage of time computing will be higher. Okay, just because the network is faster, so the communication will be faster. And I run the same code on a machine that has a more powerful computer and it is faster on the execution, but the ratio between the communications and the computation will be different. Okay? So this is not saying anything about the speed, it's just comparing how efficiently I am running, how much of my time I'm doing what I want to do, that is compute. Okay? So the result is that I have huge variability, much more than expected. Okay? Things that I expected and that I verified in this plot is that, well, communications is not a problem at all. Okay, this is a nice benchmark prepared to run efficiently. Okay, so I see some variabilities from high 80s to high 90s, but all of them good shape. Well, load balance is what I expect to have problems, but maybe not so huge number of variability on the numbers. Okay, and the power efficiency as it is the product of these two numbers. Okay, so it makes sense. But basically, if you look here, half of the machines have not green numbers. Okay, means I may need to do something to improve, but it's the same code. Okay, so the goal was can I use my performance tools to identify what's the reason of this machine that with the same code they provide these different behaviors. So things are even harder because sometimes you have even the same code, the same machine, you change some parameter and you have difference and variability. For instance, in this machine, I am using 2 different flavors of NPI. Many computers, many supercomputers have many NPI installations. Sometimes there is a default, but sometimes there are multiple versions of NPI. So you can try with one or the other, and sometimes there is a huge difference. And we will see that later on the slides. Also the binding of the processes. Okay, I'm not sure if you are used to use that, but basically in some system processes, processes are binded to the cores, so they don't move around. In some systems, by default, they are not binded, so they can be read inside the node. Okay, and also there is significant impact. And in this surprising case, if you bind the processes, then you get worse performance than if you allow them to move around. Okay, and this is just combining both scenarios, and you can see huge variability. Okay, so let's say it's not the hardware because it's the same machine. It's not my code because it's the same application. What's going on? Why I see so much variability? So I started to study the personalities of those computers. And this is, let's say, the expected one, the guy I really expected. So it's balanced. I request 27 processes, and the system automatically balances between sockets and nodes. Okay? And you can see, if I have this behavior, the efficiency is significantly in the higher score, okay? And well, what happens? I have 27. So I have, in this case, it depends on the size of the nodes and the sockets. In this case, I have 2 nodes and 2 sockets. This means I have to split 27 in 4 sets. And this means I have 3 guys, 3 sockets that have 7 processes, but one of them only has 6, okay? It's a small imbalance, but I see this imbalance. This imbalance, these are the 6 guys, the 6 NPI ranks that have more processes. They are able to run faster. And depending on the requirements of my application, this difference will be higher or smaller, okay? So if I am, the load of the socket basically will determine the data, the cache size you have available, okay? So basically, if you are accessing a lot of data, then the load of the socket will be significantly penalty the number of processes that are running on it, okay? If you don't access as much data, then you will not see so much difference, okay? So this is what I really expected, but this is quite less frequent than I really expected to see. So the best case, what is the best case? In fact, the best case, it was a lucky machine where these 27 processes fits in a node, and what does the machine, well, this is the higher score, what does the machine is alternate between the 2 sockets. So I have 2 sockets in a node, and I can fit 27 processes in a node, so I basically alternate between the 2 sockets the mapping of the 2 processes. So this is all of them in the first socket, all the ones in the second socket, and it's just automatic balancing because it's doing round robin to assign the processes to the socket. So this is another tool we have to analyze the behavior of the application. In this view, what I have is the IPC, the number of instructions, and I put here all the computing phases of my application, okay? And basically, I use this plot to compare also the execution. This is, let's say, the good guy is the one that has compact clouds with some variability, but all of the colors are quite clear. We will see now how they are spreading on the machines. So the ugly guy, what happens with the worst case, okay? This case was the same code, really the same code in a uniform machine, but now when I execute this application, I get 2 trends. And in fact, this was a training I gave the problem I have when I prepare a training, basically typically is that until the last day I'm doing things, okay? So I was working with the machine the previous day with no problems. I had to prepare my slides, and then the machine started to give me this behavior, okay? Every time I run the machine, and I run it and submit the code, I get these 2 trends. One node much more slower than the other, okay? So you see, this guy takes much more time for any of the computation. These guys have these black holes waiting for it, okay? Everything on the first node takes more to the right, larger, okay? Everything on the second node takes a shorter time, okay? So the efficiency really is under 70, so it's a very, very penalty, okay? And now you see the same plot, okay? And you see how everything is spread. So this before it was just a short line, now it's spread in 2 trends, and in fact you can identify the slow node that all the trends of the behavior are being moved to the left. Okay, so they have reduced the IPC, they have reduced the speed, the instructions are executed. But I know the machine is a homogeneous machine, all the nodes have the same memory, have the same frequency, everything is the same, okay? So what can explain that? Well, I did some checking of the clock frequency, one of the sources for variability, not so huge, but one of the sources for variability in some systems is that they modify the clock frequency, and this will reduce the speed you can execute, but this is not the case. It's a perfect vertical line, meaning all the cores from the 2 different nodes are running at the same speed, okay? So I had to start to look on the hardware counters. So this is the clustering, and I am comparing this cluster 1 with these 2 clusters, and this is the cluster 4 with the cluster 8, okay? So this is the guy that is slow, this is the guy that is fast, and let's see what the counters tell me, okay? If you have a look, I just highlight the value that is higher difference. If you have a look, for instance, with respect to the level 1, level 2, and level 3 cache misses, there is almost no difference, even if it's lower numbers for the guy that is taking more time. Nevertheless, the resources stored on the store buffer is highly increased. Okay? You may not be familiar with that counter. Basically, this counter is measuring how many cycles you are waiting on the store buffer. Okay? So it means I'm trying to write data and I have to wait. Okay, so what it's telling me here is basically the counters are telling me I do not have more failures on accessing the data. This is expected because I have the same patch size, okay? And I have the same, I have the same number of accesses to my code. I have the same code, okay? But it takes me more time to access that data, okay? To store the data. It was pity that in that machine there is another counter that is for the load buffer, but this is not available on many computers, okay? So, but we have this reference. Writing data takes me more cycles, okay? So I have the same number of failures, but writing data takes me more cycles. Mainly to guess the problem is the memory, okay? There is some problem with the memory. So I was lucky in this training, the administration of the machine was there. So as all these executions give me the same node with the same host name having the problem, I checked with the administrator that, okay, I believe this node has a memory problem. He passed some test and he found it was correct. He had having some memory problem. So he was able to reboot the node and everything was fine, okay? The problem is that the queue system, every time I request the node, I request the job, it gives me the same nodes because we're the ones that were free. So I was getting once and once the same node, and it was the same node with the same problem, okay? So I think that was a very nice idea, so a very lucky situation where I had this admin that was able to verify that my guess was real. Some other cases it's not that true, but in that case with this huge difference, this huge problem, was not a real problem of the machine. It was a problem of a temporary error on the memory of one of the nodes. So let's look at the unbalanced guide. The unbalanced guide, this is in fact the most frequent behavior. And I think this is because the administrator or the system are not really concerned, or they are not really knowledge on what means to have different sockets on a same node, okay? So this guy is just balancing between the nodes, but not between the sockets, okay? So the system is concerned to be sure that the work is balanced between the different nodes, but then within a node, there is no restrictions, and many systems first fill the first socket, and then the rest of the data is on the second socket. Okay? And depending on the size of the sockets, this creates a huge imbalance. Okay? This is one case where you already can see here these black holes. Okay? So when you see black holes on this area, means this is the real imbalance I have due to the mapping of the resources. Okay? So it's the same source codes again, and the reason is I have the typical vertical lines I showed before, except this region, meaning my program is executing the same number of instructions on each of the processes, but then the duration of the region, okay, so all of these guys execute the same number of instructions, but then the duration has these two trends, okay? And basically, in this case, well, the efficiency is going, let's say, in the boundary of the 80s, okay? And the reason is that I have to map 9 processes per node, okay? But my sockets are size 6, so I put 6 on one of the sockets and 3 on one of them. So one of them is half the size of the cache for the guys that are inside that socket, okay? And this creates this gap. If I look with the other split, or with the other picture I show you, okay, I can see they are split on the two teams for most of the regions, okay? So most of the regions suffer this different balance between the sockets, okay? And as I said, this is the most frequent behavior I have found on the machines. But I have found many other things that are also funny and interesting. For instance, what I call the bipolar machine. The bipolar machine is one that is quite nicey because you run with the given version of MPI, that in fact this was the default MPI version for this machine. This was a very large machine with shared memory, okay? Huge NUMA distributed memory, but you have access to the global memory on a large machine, okay? So the default MPI gives me this outful picture where I see much more MPI time than expected. If you remember, this is the point-to-point phases that used to be very, very thin. Okay, this is the already use. I already expected to have this imbalance from my code. Okay, and all the iterations are the same. And those means that the computing phases is not that MPI is taking more time, but the computing phases are taking more time. Okay, and if I change my MPI, this is the efficiencies are lower enough to concern about it, okay? So if I change to Intel MPI, that it was not the default, then it goes back to the Dr. Jekyll and Mr. Hyde behavior, okay? So now it's the nice guy. And this is what I expected. And now the computations, okay, are perfectly what I mostly expected. Some small imbalance due to the mapping, but quite uniform between processes, okay? And I start to wonder, okay, but let's say, I understand MPI can modify MPI, but how can MPI modify my computing phases, okay? Well, the reason basically is on the next slide. Well, the difference is 15%, is considerable difference between the two executions. And the reason is that, well, this is showing the duration of the computation is, as I said, showing the same slide, and the reason is basically on the mapping, okay? And this is defined by the MPI run command, okay? It was, as I said, a shared memory machine. Intel MPI was nicer and was allocating sockets and was trying to map things together, okay? This NPT version of MPI just spread over the machine, my processes, okay? This means each guy is running in a socket with other guys doing whatever they do, okay? Some guys have no one else in the socket, some guys have a very loaded socket, okay? So I have a very awful case. And the impact is not on MPI only, but mainly on my computations that are degraded, okay? And unfortunately, this is the default of the machine, so if you don't take care, you have this kind of behavior, okay? Next machine is what I call the undecided, and the reason for this undecided guy is that you see how, let's say, how do you identify an undecided machine? Well, you get the execution a long time, and you see some variability that is not maintained, that is different a long time, okay? For instance, here, this is one of more easily to identify cases where the first iterations, I see very noisy behavior, large MPI calls, but then a long time, they are making clean, and they are what I expected, okay? So if I identify this case, these efficiencies are still starting to be something I have to work with, okay? And the reason is that basically, during the first iteration, is doing process migration, okay? So the default is not binding the processes in many document systems, but in this case, it's not only that it's not binding the processes, that it identifies some imbalance and is trying just to balance things, okay? And in that case, the first iteration are corrupted because the system is doing not necessary migrations in the code. And sometimes you see the similar effect of this noisy behavior. For instance, here you cannot see all the iterations behave the same. For instance, here you have a black hole that is big one that is not on the other ones. So you see variability a long time. But as a difference with respect to the previous one, in this one, there is no making a clean evolution to what I expected, but keeps being noisy, okay? So this is a little more difficult case, okay? And this is I'm not sure if this is a right word in English, but it's a person that is just pushing the brake of the car, okay? So it's braking. And basically, I look at the durations here, it's difficult to identify what's going on. If I focus on my computing region that I'm interested, that is this large computing phase that I have identified is the more demanding of memory, so it's the most sensitive to the characteristics I have, okay? If I only focus on this region, what I see is some guys together that have some enlarged duration, okay? While the others keep shorter. If I look at the mapping on the nodes, I can see basically that within a node they used to have the same behavior, but between nodes they change the behavior, okay? So that's the clue. It seems that it's a kind of noise, but affects to the level of all the processes within a node, okay? So when you start to consider what happens with all the processes within a node, you can check on the clock frequency, okay? And if you check on the clock frequency, well, here, if you remember, I showed you this clock frequency slide picture for another application that was a perfect vertical line, okay? And here I see quite significant variability, okay? So if I zoom on this area, okay, then I see something that made me understand what's going on, okay? So this is the frequency of the processes, okay? And dark blue means, let's say, the normal frequency. What I have is that a long time, depending on the node, the frequency goes down for all the processes on the node, and then goes back, okay? So that's the reason I say it's just pressing the brake. It's because it's slowing down for a while, and then going back to the normal speed, okay? This case was a machine that was in a room, and it was spread, it was a cluster that it was spread, And they have problem of space, so they have to stack the computers. And the problem when you start to stack computers is that the worm of the machine, depending on where you are in the stack, is bigger, okay? And what happens with the system, well, they are nice enough to reduce the clock speed if they see they are getting warmer, okay? And this is the effect, depending where you are. So this is, let's say, the nice guy is lucky and has not to reduce the clock frequency. So this guy is getting warmer, so if you reduce the clock frequency, then it gets nice, keeps on the normal speed, gets warmer again, so reduce it. So that's the reason has this reduction. So this problem of stacking the machine identified this. This is basically creating degradation of the imbalance. Okay? If we go back, it was just not much, but it was to 75%. Okay, so let's say it's a significant degradation just due to this effect of stacking the different nodes. And this is the last case I have prepared. That is sometimes even having a nice number of processes, you still can have problems. Okay, machines are not smart enough sometimes to decide how to map the processes. So this is on a KNL machine. I request 64 processes. So 64 is a nice number. Is a cube number. Sorry, it's a cube number, but it's also a power of 2. So it should be easy to map on any system. Okay. So what happens in this system? I run on that system, and automatically it fits my application in 2 nodes, and I can realize that because I see the first guys are spending more time in MPI. They have more colored pixels here. Okay, if I look at the duration of the computation, I also see the second guys are doing longer computations. I can verify that the mapping corresponds to the different nodes. Okay, in this case, the efficiencies are still good enough, but there is some small inefficiency. Okay, and I see these 2 trends that depends on the mapping on the nodes. But each node has 32 processes, and they are the same mapping on the different sockets. So what's going on? Well, the reason here is you have to check on the other counters. I have not included that information here, but basically identify the 2 trends, as we said before in the other case of the other guy. Identify the 2 trends for the different code regions, and the reason here basically is that this is a machine that has 2 types of node. One of them has more memory than the other, and by default, it provides you 1 node of each type. Each type, okay? So when I say to the administrator of the machine, okay, this is a bad idea, because basically you are giving to the users an unbalanced machine, they say, well, they have to specify what they want, okay? But if this is not the case, if you forgot to add this, what they want, to specify, I want either the small ones, the small memory nodes or the large memory nodes, you will get 1 of each of them, okay? And in this case, basically it was between 15–20% of reduction of your time. So that was my last scenario. So the idea is I have tried to explain you different machines with the same code behave differently. My conclusions for this talk, basically, if you are a programmer, is, well, do not consider machines will do a good job with your applications, even you have been working hard to have a good job, a good application that may perform perfectly. If you want to analyze the code, you have to be flexible. You have to have tools that allow you to not to not to decide where are the problems, but to help you to guess where are the problems. Okay, and as Bruce Lee said, you have to adapt and you have to be water. Thank you very much. If you have any questions.